All right.
I'm going to come to you for physics.
Okay, so here's the deal. I've graded everything I have. I posted the grades today. The mini exam 5, I did not count number 8. Unless you did it, then it was worth a bonus. So I only counted 7 problems. Each problem is worth 10 points. So if you see on here like you had a total of like minus 10 points, then you got 60 out of 70 points. Create the ratio, that's your grade. Then if you did the 8 and you got it right, then I added 10 points, so it would be 70 out of 70, which would be 100. Make sense? So when you get these back, there's no grades on them. It's just how many points I took off. And then I've updated the grades online. I do have, you might have 2 things in here, but I did put them in order, so all of yours should be together. Okay, so please just pass this around. Yes? Yes, I remember that. Yep.
Where did you add it?
Oh, I haven't added it. Yeah. I actually have a couple of bonuses from this class. The ones you're talking about are sitting in my inbox in a special folder that I need to go and look at. And the ones that you handed in are actually taped to my wall in front of my desk. So I'll get to it. Don't worry. Yeah, I have not applied those to anything. I also I did one problem today for online videos for homework. I didn't give you a homework assignment out of 12.4 last time. I gave you a homework assignment out of 12.3. Actually, I emailed everyone because it was at the end of my notes. But for 12.4, what I'd like for you to do is it's actually 2 problems. It's page 720. This is out of 12-4. And number 12 and number 18. Now, those are both even problems, so you can't check your answer, but I did that online in a video. This is a problem where you have to find the center of mass, the center of mass, and the moments of inertia for some lamina. So I talked about it at the very end of class. I didn't get into it. This is an example for you. All right? We good? Okay. All righty. 12.5. So we begin today with triple integrals. So I thought I would take just a quick, brief moment to remind us of kind of like the progression of things here. In Cal 2, we did a regular integral like this, right? And we found the area underneath this. Yep. And so if I ask you here, what is our region of integration? What is our region of integration? What are we integrating over here? You would have to look to the dx to give you some idea of that's the part that tells us about the region. And therefore, it's actually this little line segment, that interval AB. Right? So in a Cal 2 integral, when we're integrating a function with respect to x, our region of integration is a line segment. And line segments are one-dimensional, right? One dimension. Here, last class, we started doing these double integrals, right? And it was like double integral f of x, y, dA, and it was over some region d or r, right? That's what we were using. And so I say, well, what's the region of integration here look like? So you say, all right, well, where did this dA come from? That was the ground, wasn't it? And so that region on the ground was two-dimensional, wasn't it? And that was kind of a difficulty for us, right? Because when we have a two-dimensional region, we started to think about all these complexities we could get here, and so we said, look, let's try and classify these regions. We had type 1, type 2, and then we converted over to polar, right? Well, we had rectangles, which was the easiest, right? Then we went to type 1, then we went to type 2, and then we went to polar, yes? Today, we're going to look at triple integrals. And it's going to be some function of 3 variables that we're integrating. And it's going to be with respect to, let's try and guess. This is dx, x is one-dimensional, just the length of this line segment. dA was the area, which was a region in 2-dimensional space. And this maybe will be what? Volume, right? Some volume of something. It's going to be dV. And so our region of integration is actually going to live in 3-dimensional space. It's going to be some solid here. Now, do not make this, do not confuse this with what we did last time. Last time we were finding volumes of solids between 2 surfaces, right? Yes? The surfaces came from this piece, because we could draw that function and we could have like the top cap and the bottom cap. The ground would be the region of integration. Here, this function takes in 3 inputs and spits out an output. I can't show you this function. We aren't going to be able to see it, all right? So what we will be able to see is its region of integration, but that's it. Do you understand the difference? Pardon? The domain, yes.
The domain of it is going to be a plane.
The domain of a triple integral is a solid in 3-dimensional space. The domain of a double integral is a flat surface in 2-dimensional space, and the domain of a traditional integral from Cal 2 is going to be just a line. So 1-dimensional domain, 2-dimensional domain, 3-dimensional domain. See the difference? Okay. So if you might imagine these probably even more complicated than these, right? We had enough of a hard time dealing with this, right? Now we have a 3rd dimension. So where should we start? Where do you think we should start to make things simple to start with? Like a cube, right? Like a nice box. That's the most simple solid we're going to be able to deal with. So that's where we start today. And very quickly, we're going to realize that not only do these objects get hard to represent, we're going to need additional coordinate systems to do it. So like in double integrals, we use polar to help us out. And so we're going to have to use some more coordinate systems. So we'll have 2 additional coordinate systems that we'll use, cylindrical and spherical. But we'll get to that when we get to it. All right, so triple integrals. A triple integral over region E. So we call that region the domain E. And in this case, let's look at how we are defining the E. Okay, E is a box where your x coordinates are bounded between 2 constants, the y coordinates bounded between 2 constants, and the z coordinate is bounded between 2 constants, r and s. So if I take away this, that was the rectangle from a double integral. We've added in a 3rd dimension and bounded the z between 2 values. And this is what it looks like. Right? So the x-axis is here, the y-axis is here. Here's our box sitting in 3-dimensional space. Does everyone see that our x values are stuck between 2 places? Our y values, so these are x values. Our y values are between 2 places, but now our z values are stuck between 2 constants. Notice that if you take this box and you look at the shadow that it casts onto the ground, all right? So imagine you have a light source up top, and you cast this shadow down. What does the shadow look like on the ground here? That looks like the region that we dealt with double integrals, isn't it? Isn't that just a double integral region? That would be a rectangle from double integrals. Now that's important because of where we're kind of going with this. What's on the ground is going to help us be able to do triple integrals, seeing the shadow on the ground. No questions on this though? Pretty clear? Okay, so if that's our region of integration, what does the triple integral turn out to be? So we have 3 integrals now. We're integrating over that box. We're integrating a function of 3 variables, which I cannot draw for you. Sorry, okay, can't do it. And we're integrating with respect to volume. So that little dv thing, I don't know if I can do this. I don't want to waste too much time, but well, in 2-dimensional space with double integrals, we cut the region up into little infinitesimal pieces, and each one of these little areas was dx dy, wasn't it? And that little dx times dy represented our dA from our double integral. Now, our region that we're cutting up, since it's 3-dimensional, this is a box, but I'm taking a little slice of it, but I'm taking a little cube out of it, like a little sugar cube, right? I'm saying, what's the volume of that little infinitesimal cube? It should be dx dy dz, right? Or dy dx dz, or dz dx dy. How many different combinations are there? Well, let's start with the easiest, okay? The easiest one is to go dz dy dx. This is the way you do it if all your variables are bounded between 2 constants. Can we change the order of integration? Could we change the order of integration when we had constants in double integrals? Yes, right? So it's the same thing with the triple integral. If you have your 3 variables are bounded by constants, then you can actually write this out dz dy dx, or dz dx dy, or dx dy dz. There's 5 others, so 6 total triple integrals you could do over a box. Your choice. So let's do this one. Evaluate this triple integral, x squared y z dv on 0, 2 crossed with 1, 2 crossed with 0, 1. So these are our restrictions on x. These are our restrictions on y. These are our restrictions on z. That's a box, so I can use the formula I just had up there. I'm going to choose to go dz, dy, dx. That's just my decision. What is it that I am integrating? X squared yz, right? And then my limits of integration, I'm going to go 0 to 2 here. That's my x's. 1 to 2 here, that's my y's. 0 to 1 here, that's my z's. Now, like we did before, we started from the inside and worked our way out, right? So I'm going to go with this inner integral first, and then work my way out. So this should be equal to antiderivative of x squared yz with respect to z is what? 1 half x squared y. I didn't hear you. Z squared. Okay, everyone agree? Evaluated z equals 0 to z equals 1, right? That's the inner integral. And then I'm going to have to, after that, do dy dx. So do you already see that this is exactly what we've done? Just we have one additional integral that we have to do. One additional variable to deal with. All right, let's let z be 1. Nice. Z is 0. Even nicer, right? So this will turn into double integral 0 to 2, 1 to 2. And 1/2 x squared y. That's all we're left with when we plug in 1 and 0. D y dx. And now you're pretty much at what, last class, at the class before, right? You're now at a double integral. So you just go the rest of the way with this. Okay? Just one little additional step. Now, these are the least complicated triple integrals you can ever get. So, of course, we were going to have to make it a little more complicated, right? Any questions, though? Yes?
Are we always going to be given Z? Since, like, if you look down at the domain region, you really can't tell what Z is for the
Are we always going to be given Z? How do you mean?
the bounds for it?
This?
Yeah.
Oh, no. See, because this is like, again, remember this domain, this E right now is a box. We want our domains to be things that are more interesting than boxes. And so like, take a sphere in the first octant, just that first octant part of a sphere or a ball. You take a ball and just take the piece that's in the first octant. I want that to be E. How do we integrate over that? Because you can't say x and y and z are all between three constants because it's not a box. So that's what's more interesting to us. So we'll see. Hang tight. You'll see how that's going to work out. Actually, it's going to happen like right now, too. All right. All right, so how about a triple integral over region E? So we have a solid, right? I'm not going to tell you exactly what it looks like, but here's what I will tell you. If you take this solid and you cast its shadow down onto the xy plane, its shadow is a type 1 region from a double integral. So here's what I'm talking about. Whoa, why is that so big? Here's what I'm talking about. I have a solid up here, okay? And all I'm telling you right now is that when you cast that shadow down to the ground, that region on the ground is type 1. I mean, that's not working. Screw it. Sorry, I'm trying to rotate this damn thing so you can see it. All right, that's good enough. Is that a type 1 region from a double integral? X is between two constants, y is between two functions of x. Actually, I think I need to reevaluate this. There we go. Okay, so I'm back on the ground. That's type 1. I'll show you our x labels. So our x's are between a and b. Our y values between two functions of x. And now I'll show you the region. I was hiding that from you, okay? But there it is, okay? Do you see, from the top, that's how I get that region, the shadow on the ground. But the z values, okay? The z values are actually stuck between what? Two functions of x and y. See, this is a surface, isn't it? So it's a function of x and y. This is a surface, so it's a function of x and y. So your x's are between two constants, your y's are between two functions of x, and your z's are between two functions of x and y. That is the type of region we're interested in integrating over, at least to start. So this is the way we look at that region. And this is just what I had down here. A is between two constants. Y is between g1 of x, g2 of x. And then z is between two functions of x and y. So we call them, normal notation, u sub 1 of xy, u sub 2 of xy. If that's your region, if that's what it looks like, then here's the formula for it. the triple integral of some function, oops, that's supposed to be x. The triple integral over the region E of the function of three variables with respect to volume is, well, let me get to this. This is nice. You're integrating the function dz, dy, dx. That's the order, right? But look at your limits of integration, right? They're function, well, except for this. This is constants, functions, functions, right? Do you think you can change the order of integration? No. No, you can't. You have to do it this way. All right, this ought to be fun. Evaluate the triple integral of what function? Y. That's it. The function of three variables up here is just the y function. Nice and clean and easy. dv, where E is bounded by these planes. So we've got to figure out what E looks like first, right? So let's try and draw E. And I've got to try and draw this in three-dimensional space. X, Y, Z. What is x equals 0? X equals 0 is the YZ plane. It's the ground, right? I'll just draw it out here first. There's the ground, right? Hold on. I drew the wrong one first. X is 0, YZ plane, back wall here, yeah? Then Y is 0, XZ plane, which is this wall over here. Kind of closing off the first octant here, aren't I? And then Z equals 0, which is the ground. And then the plane 2x plus 2y plus z equals 4. How should I draw that here? What would be the easiest way to draw that plane? Solve for z, like just move everything around and solve for z? We could do that. Yeah, I like that idea, but we can also, how many points do you need to define a plane? 3 points, right? So just let's find, how about where the plane hits the axes? So where does this plane hit the x-axis? How would you determine that? You set y and z equal to 0, right? So go into this plane, set y and z to 0, and you get 2x is 4. So x must be 2. So I know that one of the points on my plane, which I'm out of colors, so I'll just do it in black, is 2 on the x-axis. How about where it hits the y-axis? Set x and z to 0, right? And get y is 2 also. And finally, to figure out where it hits the z-axis, let x and y be 0, and you get z is 4, which is up here. I have a plane that goes through those 3 points. So what I'll do is I'll connect the 3 points together like this. Do y'all see the solid? Do y'all see that solid? That's E. Does the shadow of E on the ground look like a type 1 region? So let me now look at the XY plane, the shadow on the ground. I hit here at 2, right? Was 1 point. That's this one right here. The origin is this back point, so that's there. And then 2 here. So wouldn't that be the ground? Wouldn't that be this piece right here? Yeah? Now I've turned it so we can orient things the way we're used to seeing them, is that a type 1 region from double integrals? Yes? Yeah, because if we drew, the way we did is we said if we drew an arrow from here to here, and as long as the one on top and the bottom stayed the same as we move from left to right, then it is. But I actually need to know what that is, don't I? Don't I need to know what this function is? This function here is my g sub 2 of x, and then the bottom one is my g sub 1 of x. Do you all follow that? What is g sub 2 of x? Negative x plus 2. How'd you get that? You just looked at it, right? I mean, this is a line, right? Y-intercept of 2, slope of negative 1. The other way you could do that, though, that's the way I would do it. But keep in mind, the other way that you're doing that, or can do that, is that line is this right here, right? And that's where that plane hits the xy plane, right? When you hit the xy plane, z is 0. So if you go back up to this plane and you let z be 0, you get 2x plus 2y equals 4. If you solve that for y, you will get this right here. Understand that? I only say that because if it wasn't as simple as a line, then that's what we would have to do. Questions?
Could you repeat what you just said about solving it?
Okay, yes. So if I have to first understand that this line right here is this line, right? And this line is where that plane hits the xy plane. Anytime you hit the xy plane, z is 0, right? So if I take this right here and I let z be 0, let that z be 0, it's not there, and I solve this for y, you see it? You would get the linear equation which represents that. Okay? All right. Can you tell me what the restrictions on x are here? 0 to 2? So here's what I got so far. I've got x is between 0 and 2. I've got that my y is between what? 0, right? This function here is a flat horizontal line. And then the one up here, negative x plus 2. So this is going to go from 0 to negative x plus 2. The last thing we need to figure out is what our restrictions on z are. And this is where we have to look back to the 3D picture, and we have to figure out what's the top surface, what's the bottom surface. So, bless you, what is the top surface for this region E? It's the plane, isn't it? The plane. This triangle basically is the top of the solid. So how am I going to write that plane as a function of x and y? Solve for z. So take this right here. Now I'm going to draw it. This arrow is representing this surface right here. That is z equals 4 minus 2x minus 2y. Do you agree with that? Now, in terms of the formulas that I just gave you, or from the notes, I know it's hard to see. Our y's, I said, were restricted between g1 and g2. That's why I wrote g1 and g2 here. Our z is restricted between u1 of xy and u2 of xy. So this one is actually u1 or u2? u2, because it's the one on top. So this, I'm going to replace the z here. I'm going to say this is u2 of xy is that top surface, which is the plane. And then what is the bottom surface? What's the bottom of that? It's just the xy axis. I mean, xy plane, isn't it? The equation of the xy plane is z equals 0. But that's my u1 function. So u1 of xy equals 0. Understand? And so I can come back over here now and I can say z has to be between 0 and 4 minus 2x minus 2y. How are we feeling about that? All right, so we got to set it up now, right? I need to erase, so I'll give you about 4 more seconds. All right. So I've got to do a triple integral. My limits on x were 0 to 2. My limits on y were 0 to negative x plus 2. My limits on z were 0 to 4 minus 2x minus 2y. Right? What function am I integrating? Y. With respect to z, y, and x. That's it. That's the setup. And now we do the integration. So I'll do the inner integral now. Do this one. The antiderivative of y with respect to z is yz, right? I said yz, I wrote xz. And then from where? Z equals 0 to z equals 4 minus 2x minus 2y, right? That's what I've got to do. And then I still will need to do dy dx after I'm done. So replace z with this, and then we replace z with 0. Thank goodness for the 0, right? I don't have to worry about that. So just z right here. So we will have equals integral 0 to 2, integral 0 to negative x plus 2, and then what happens if I replace z with that and distribute the y? What do I get? Over y is 2xy minus 2y squared. Yeah? dy dx. And now that is basically what we did a couple of classes ago, right? Should I dot dot or you want me to go all the way? I don't care. It's up to you. So let's take a vote. All the way?
One more step.
One more?